Welcome to the second video. In this video, we are going to derive the continuity equation. But before we can start with this, we first have to remind ourselves that the continuity assumption holds. The continuity assumption states that fluids can be described as a continuum and can thus be divided into infinitesimal volumes. We discussed in the previous lecture that this assumption holds even for the case of microfluidics. So keep in mind when we are deriving the continuity equation or later the conservation of momentum that we always assume that we can describe our fluid as a continuum. When we want to derive the continuity equation, we consider an infinitesimal small control volume, which is illustrated on the right. As you can see, it has the shape of a cube with the dimensions dx, dz, and dy. We can now state that the change of mass inside the control element equals the difference in the mass flow over the element surfaces. The change of mass inside the control element can be described by the partial derivative of the mass m with respect to time. And we can now reformulate that by substitute for the mass the density times dx, dy, dz. So the change of mass inside the control element can be described by this term. As a next step, we have to think how we can describe the mass flow over the element surfaces. To be able to evaluate the mass flows over the control element surfaces, we first have to look at the mass flow itself. Mass flow can be expressed in different ways. It can be expressed by the density times the volume flow, or the density times the cross-section times the velocity of the flow. And if we now want to look at the mass flow, we first only concentrate on the x direction. So we make this a one-dimensional problem to understand the concept. If we now look at our control volume, which can be seen here, we have to evaluate the mass flow over the surfaces which are perpendicular to the x-axis. So in this case, it would be this surface and this surface, because only those surfaces are perpendicular to the x-axis. We start with the left surface. Here, the mass flow inside our control volume can be simply expressed by the density times the volume flow in x direction. On the other side of our control element, volume flow will leave our control volume. And here we have the same term, the density times the volume flow in x direction, plus an additional term. And this additional second term equals the change of the mass flow in x direction inside the control volume. This is this term, so the partial derivative of the mass flow in x direction with respect to x times dx, because dx is the distance over which this change happens. So if we now balance those two terms, we can write down the mass flow balance in x direction, which reads like this. In a very similar way, we can also analyze the mass flow balance into all three directions. This is done on this slide. While it looks complicated at first, it follows the very same pattern. You have the two terms we already discussed, which enter through this area and leave through this area. So you already know those two terms. Now we do the same in the y direction. We have mass flow entering via this surface control element area, and we have a mass flow that leaves our control volume via this surface. And the same can be done for the z direction. Here we have to use this element area with the corresponding mass flow and this element area with the corresponding mass flow, this one. And if we now write down the mass flow balance, you see that this is a lengthy expression, but it's nothing different from what we have done so far. So the left-hand side of the first equation is the mass flow balance over all three dimensions. And the right-hand side is the change of mass inside the control element. And what we have done here on the left-hand side is we have replaced the volume flow by the area and the velocity. So note that those y's are small y's. They denote the velocity component and not the volume flow anymore. And if we multiply the velocity component with the cross-sectional area, we get the volume flow, which in turn, if we multiply it with the density, becomes the mass flow. And if we simplify this mass flow balance, the simplified expression reads like this, which is the differential form of the continuity equation for a Cartesian coordinate system. And if we now write this in tensor notation, we end up with this equation. As a next step, we want to take a closer look at the continuity equation and discuss the physical meanings of the individual terms. For this, we first have to do some transformations. We start with the continuity equation and apply the product rule, which will yield the second equation. And now we can use the first two terms to combine them into the total derivative of the density with respect to time. The physical meaning of the different terms is quite simple. The first thing you have to know is that this expression is called a substantial or material derivative. And it consists of the local derivative, which is the first one, the first term, the blue one, and the convective derivative, which is the second one, which is indicated here in red. And the substantial derivative is the total derivative with respect to time. So you probably know this already from math courses. And the physical interpretation is this. The substantial derivative gives the time rate of change of a function f as the observer floats along a path line in a flow attached to a fluidic element. As an explanation, there's a figure on the right-hand side. Here you have a fluidic element, and this fluidic element is now not fixed in space. Instead, this fluidic element can follow a path line. A path line is the line on which molecules flow in a flow field. So the fluidic element is following this path line, and if we now have the total derivative or the substantial derivative, then we have the total change inside this control element, which is now moving. We still haven't discussed the physical meaning of the second term. For this, we first bring it to the right-hand side. So this is actually a notation you will find quite often in literature when looking for the conservation of mass. And the physical meaning of the right-hand side is quite easily explained. As you can see, the right-hand side consists of the divergence of the velocity field. And the divergence of a velocity field is the extent to which the field behaves like a source or a sink. This is illustrated on the right-hand side for three simple cases. In the first case, you have a source. So here's the source, and as you can see, the velocity field is pointing away from that source. So here, fluid enters, and we have a source. The divergence of this system is larger than 0. The opposite is the case in the second picture. Here we have a sink and the expression becomes negative. And in the third case, the expression becomes 0 because we have neither a source nor a sink in our image. This is the final expression of the continuity equation, and you should be aware what the physical meaning of the different terms is. And there's one more simplification we can assume. For incompressible flow, we can always state that this term becomes 0. So keep in mind that if you have an incompressible flow, and we are mostly dealing with incompressible flows when we are dealing with liquids, the continuity equation can be further simplified.